Hi everyone, and welcome back to Physics 11. So in this video we're going to be looking at power. So power is the rate of doing work. So we've talked about energy and work. So for example, what happens when you're doing work over time? For example, like you might be running, or maybe the engine of a car is spinning constantly as you're driving. So it's constantly outputting some sort of energy as it over time. So again, power is going to be the rate of doing work. So we're going to be expending or consuming energy over time. So power, again, in everyday language is often kind of used interchangeably with work and often being thought as the same thing. But in physics, these are not going to be the same. Okay, so whenever we talk about work, we're not concerned with time. Okay, so that could be just an instant in time, or we don't really care about the time anyway. We're just talking about either final or initial energy amount. So when we're talking about work or change in energy. But when we talk about power, we are looking at the change per second. So we have this rate, so joules per second, or the unit watts, which you, for example, see in light bulbs. So for example, the measurement of a light bulb, say 60 watts, means that the light bulb consumes 60 watts every second. So the equation for power is going to be then the work done over time or the change in energy over time. Okay? So here's an example. We have Lover's Leap, which is a cliff, 122 meters, vertical climb. The record time for this climb was 4 minutes and 25 seconds, was achieved by Dan Osman, whose mass was 65 kilograms. What was his average power output during the climb? So as he was climbing, of course, he's using energy. His muscles are using energy, so he needs to expend energy in order to climb vertically up. So in this case, we have something like this, right? This is going to be our height, 122 meters. So we're starting at the bottom here, right? So he's going to climb all the way to the top. So it's a vertical climb. So our power output is going to be work over time. But in this case, we're looking at the change in energy over time. And because this is going to be working against gravity, this is going to be change in potential energy, so EP. So we can expand this and say, okay, potential energy is mass times gravity times height. The only thing that's going to change here is going to be our height. So you're going to go from 0 to 122 meters. So we can expand this to mg delta h over time. And delta h is going to be our final minus initial. So we can expand it one more time. So here we have hf minus hi over time. Now notice here that our time is given in minutes and seconds. So there's one step we have to do before we can calculate the power output. We need to convert the minutes and seconds to just seconds, because remember, in metric units or SI units, we need to have seconds as our time. So let's convert 4 minutes to seconds. So every minute has 60 seconds. So we have 4 times 60. So that's going to be 240. And then we had to add the 25 seconds. So 4 minutes and 25 seconds is going to be the 240 seconds plus the 25 seconds, which is going to be 265 seconds. So that's going to be our time they're going to plug in here in our power output calculation. So the mass of the climber is 65 kilograms. Notice that HI here, once you set it to 0, we can actually reduce it away. So all we're left with is just the H final. The gravity is 9.8, and H final is going to be 122 meters over the 265 seconds. So 65 is our limited number of sig figs, so 2 sig figs. So our final answer is going to have 2 sig figs as well. So in this case, the answer is 290 joules per second, or watts. So that means that for every second, the climber was outputting 290 joules. So remember, or you can say joules per second. So that's maybe easier to understand, because for every second, the person has to expend 290 joules of energy. Okay, so other measures of energy could be calories or kilocalories. In this case, we're using joules. So you can always convert. For example, if you're eating something, we'll have the energy unit measured in calories, but you can convert it to, or rather kilocalories, you can convert it to joules. So this is an example with change in potential energy. So let's take a look at an example where we have change in kinetic energy. So in this example, we have 1,000 kilogram car accelerates from rest to a velocity of 50 meters per second in 4 seconds. So calculate the power output of the car, ignore friction. So again, our power output is going to be work over time. In this case, we're looking at change in energy over time. And because we have a moving object, we're talking about kinetic change in energy. So it's going to be delta EK. So in this case, we can expand this. So we're going to have our final kinetic energy minus initial kinetic energy. So this is going to look like 1/2 m v squared, but in this case, we're going to look at delta v squared over time. Now your delta v squared is going to expand as, if we factor out the 1/2 m, we're going to get vf squared minus vi squared here over time. And again, because we're starting from rest, our vi is going to be 0. So that reduces away. We're left with just the v final squared. So that's going to be our equation. So 1/2 m vf squared over the time. Now, in this case, the time is already given in seconds, so we don't need to convert it. All we had to do is just plug in the values. So let's plug in the numbers, and let's see what we get. 1/2 times the mass, which is 1.0 times 10 to 3, times the velocity, which is 15.0 squared. Don't forget to square the velocity over the 4.00 seconds. So in this case, we have 3 sig figs in every value here, in every variable. So the answer should have 3 sig figs. So once you calculate this, you're going to get 28,100 joules per second, or watts. So in this case, the car outputs 28,100 joules every second that it accelerates for the 4 seconds. So here's an example. Again, this is an example with kinetic energy, and the previous one was with potential energy. But what about work? So let's take a look at another useful formula. So we know that work is force times distance. So power is going to be then force times distance over time. And we also know that velocity is distance over time. So as you can see here, we have this d over t that we can replace, substitute into here. So basically what we can do is replace d over t with the v, and we're going to get this equation, where power is going to be defined as the force times velocity. Now notice here that this velocity only works for constant velocity. Okay, so if you have, for example, initial velocity and final velocity, this equation isn't going to work. Okay, so this only works for constant velocity. So here's an example where we have a student who uses 140 newtons of force to push a block up a ramp at a constant velocity of 2.2 meters per second. What is their power output? So we have some ramp here, and again, in this case, we don't really need a free body diagram, but just to visualize what's going on here, the block is being pushed this way at 2.2 meters per second with a force applied of 140 newtons, right? So what is the power output? Well, we're going to use our new equation. Power is going to equal the force times velocity. Plug in the force value. So that's 2 sig figs, and the velocity is also 2 sig figs. So the answer is going to have 2 sig figs. So that's going to be 310 joules per second, or watts. Okay, so there you go. This is a useful equation that you can use in case you're looking for the power output and you're only given the force and the velocity that the force is being applied at. But again, remember that this only works for moving objects. at constant speed, so constant velocity. So if you have, again, different initial final velocity, you cannot use this. So that's it for the power section. There are 4 questions that you can work on and just below the notes. And again, the answer key is at the bottom. If you have any questions about any of those examples, make sure you post a comment as a reply in the Teams.